Hello, this is the video presentation for the ECE176 final project. My name is Rohan Gujral, my partner is Brett Kinsella, and we focused on our attempt to recreate a famous research paper that had to do with image painting with context encoders. This was contributed to by several professors from UC Berkeley, and in summary, they attempted to train various models to predict how to fill in certain images with various methods, one of them being context encoders. Although image inpainting seems commonplace in many modern devices such as smartphones and computers, this problem was once at the forefront of artificial intelligence and machine learning research. As a matter of fact, the paper we are trying to re-implement itself was originally published in 2016. One thing to note is that although their implementation uses the CAF framework, our implementation was solely in PyTorch. In the paper, they describe two distinct models, one using reconstruction loss alone, and the other using a linear combination of both reconstructive and adversarial loss. One thing it is important to note, though, is that the inputs to these models are very different. One of the key challenges with a project such as this is to be able to source gold standard data. For our project, we sourced a publicly available dataset from Kaggle, which contains 12,000 images of landscape data, which was pre-categorized into 5 distinct groups, namely coast, desert, forest, glaciers, and mountains. This ensured that with various inputs, we increase our likelihood of increasing our accuracy when performing testing and validation. More specifically, the dataset contains 10,000 training images, 1,500 validation images, as well as 500 testing images. Unfortunately, however, the image dimensions were not standardized, so we had to make sure that we standardize our images to either 128 by 128 or 227 by 227 to be trained for their respective models. The first model we decided to implement was the semantic inpainting model. This model uses a joint loss function combining both adversarial loss and reconstruction loss. We did not modify this architecture from the research paper to be able to compare it as best as possible. This model takes in a 128 by 128 pixel image whose center region has been removed and filled with a constant mean value. The encoder consists of 6 different convolutional layers, and each layer reduces the spatial dimensions while simultaneously increasing the amount of feature channels. In our case, we use a kernel size of 4 and a stride of 2. As per the original implementation, we used batch normalization after each layer, except for the first layer, along with using a leaky ReLU nonlinearity function with a negative slope of 2. The next model we tried to implement was the feature learner model. It is important to note that this model only uses reconstruction loss instead of using a joint loss function. Also, we did not use central blocking, we instead used random blocking. This also ensured and protected against the model learning lower level features. One major difference as well is that this model expects 227 by 227 dimension input images, and it processes them down to a 6 by 6 by 256 dimensional feature representation. The kernel dimensions in stride are 1 by 1, and the stride itself is also 1. The decoder uses 5 fractional convolutional layers with a kernel size of 3 and a stride of 2 to progressively upsample the 6 by 6 feature representation we mentioned earlier to a 161 by 161 feature representation. During the training process, we utilize the AtomW optimizer instead of the traditional Atom optimizer used in the original implementation. We also used a one-cycle learning rate scheduler to improve convergence speed. Overall, both models were trained for 100 epochs each with a batch size of 64, and at the end of each epoch were validated against the aforementioned validation dataset. Both models were evaluated using reconstruction loss, L1, L2 loss, peak signal to noise ratio, the structural similarity index, and the semantic inpainting also was evaluated on the adversarial loss, join loss, and discriminator loss.